This is problem 25 of the QHack 2023 Quantum Coding Challenges, and this one is entitled Unitary Operators and Beyond. Now in this problem, what we're being asked to do is to come up with a way to implement a circuit that would apply the sum of unitaries. So we know that when we have a quantum circuit, if we have several unitaries, what we get as an overall block is the multiplication of those unitaries. But we're being told that we need to find a way to apply actually a sum of unitaries. Now, this problem is relatively easy because they give us already the circuit that we need to implement. So all we need to do is code this up. But I thought it would be interesting to just describe why is it that this circuit works. So again, what we're told is that we need to implement a circuit, and here I'm just denoting it as this box here, that applies this lambda to a quantum state. And that lambda is basically the sum of a unitary u and a unitary b multiplied by some prefactors alpha and beta. Now u and v are unitary matrices, but that doesn't mean that the sum of them is going to be unitary, particularly if we do this linear combination where we're multiplying with some arbitrary values of alpha and beta. The sum in general will not be unitary. So how do we go about implementing something that could apply lambda to a quantum state? So what we're told is that we can implement the application of this lambda probabilistically if we add an ancillary qubit to our system. So basically here we're doing it for a 1 qubit state, and here it's denoted as an input psi. And if we add this ancillary qubit on the top, which we're initializing as 0, using this circuit, we can find that here at the output, we will have the state lambda psi up to some normalization factor. Because as we said, lambda is non-unitary, so just multiplying psi by lambda wouldn't preserve its norm. So this is going to be up to some normalization. But again, how is it that this works? So let's go here step by step and see what happens throughout the circuit. So the first thing we have here is at the input, just the tensor product of state 0 with state psi. Then this unitary W of alpha and beta is given by the following matrix. So we have these coefficients alpha and beta that are real positive numbers. And if we construct this matrix, when we finish the execution of this circuit, that is going to allow to have this linear combination of alpha times u plus beta times v. So here all we have is each of those coefficients, but with a square root, and then some normalization of 1 over square root of alpha plus beta here, pre-multiplying the matrix. Now, if we apply this w to this auxiliary qubit that is initialized at 0, well, all we have here is basically, again, at the bottom, we haven't applied anything, so we still have our state psi. And then at the top, well, if we are passing state 0 to this, all we get is the first column of this matrix. So basically, square root of alpha times 0 plus square root of beta times 1, right? And then our normalization constant here at the front. Next, what we do is we apply the unitary u to state psi if the top qubit is 0 and the unitary v if the top qubit is 1. So what we're going to have after applying these two gates is going to be, again, the state square root of alpha 0. And now here for psi, well, we have u of psi, and then square root of beta times 1, and then v times psi. So all we did was we replaced our state psi here by the application of u when the auxiliary qubit is 0, and the application of v when the auxiliary qubit is 1. Okay, and then the next step is to apply the conjugate transpose of this matrix W to that auxiliary qubit. Now this is going to generate the following state. We get that when we have the state 0, the bottom state is precisely what we're looking for. So we get psi times alpha u plus beta v, which was what we wanted to obtain here, right? We wanted to get a state that was psi after applying this lambda, right? Which was alpha u plus beta v. And this is precisely what we have here. obviously, as I said, up to a normalization factor, plus this other part of their superposition where we get state psi after applying v minus u when we have the state 1 in the auxiliary qubit. So if now we perform a measurement, every time we measure the state 1 on that auxiliary qubit, we can discard our result. But if we measure our 0, then we can keep that bottom qubit, and we know that it will be psi times that linear combination of u and v. Now, if you're wondering how did we arrive to this expression here, I'm not going to go through all the details, but I'm going to show you here all the steps in case you want to pause the video and see how to derive this equation. So here is the state before applying that transpose conjugate of w, and then here are the steps that we need to follow to arrive to that final expression where we get here, when we have in the auxiliary qubit 0, the state psi times that linear combinations of the unitaries u and v. Okay, and now if we perform a measurement here on the top qubit, as we said, with some probability we're going to measure state 0, and with some probability we're going to measure state 1. And if we measure state 1, we discard the result. If we measure state 0, then here at the bottom we're going to have that lambda psi state. And basically that's summarized here. So with probability of alpha squared plus beta squared over alpha plus beta squared, we get the state of interest. And then with probability 2 alpha times beta over alpha plus beta squared, we get the state that we're going to discard. Now, here I have already renormalized the states after performing a measurement. So it's basically just taking that output state we had over here and dividing by the probability amplitude of obtaining the state, and same here. The details of that normalization are here. So here we have the state we had before measurement, and this is just basically taking the square root of the probability of finding that state, and then same here at the bottom. This was the state, the portion of the state pre-measurement, and then down here is the normalization, which is just the square root of that probability, and that gives us our normalized states if we measure 0 or 1. Okay, so that's it. So let's now go ahead and implement that circuit in PennyLane. So we import PennyLane and NumPy. Then we're going to implement a function that generates that W matrix that we had. Now we're going to define our device on our Q node, which we're going to call linear combination, and takes as an input U, V, alpha, and beta. So the first thing we do is we apply that W gate on the auxiliary qubit. Then we apply our control gates U and V. And for the control U gate, we use the control wire is qubit 0, the target wire is wire 1, and then the control value is 0. So that activates that gate if the auxiliary qubit is 0. And then for the control unitary V, it's the exact same thing, but that gate gets activated when the control qubit is 1. And then we need to apply the transpose conjugate of that unitary W. So we use the QML adjoint function in PennyLane to do that. And then we're being asked to just return the probabilities of the auxiliary state. Okay, so these are the inputs that are given to us for the unitary U, unitary V, and alpha and beta. So if we now both print our circuit and the output, here we can see that we have a unitary that applies that W gate, the control U, the control V, and the transpose conjugate of that W gate. And then we get probabilities of 0.89 and 0.109. And what the grader is checking is just this one probability of measuring 0. So if we go here to the results, we see that for those inputs, this is the expected output, which matches what we got. So I hope this was helpful. Let me know if you have any questions.